This video is going to review how we came about the functions that we did for solutions to the particle in an infinitely deep box, as well as the corresponding energy levels associated with those functions. So to start, and this is the way we're going to want to start every single problem here in quantum mechanics, is we're going to evaluate the Schrodinger equation. So I have the Schrodinger equation up here written out in a form such that we have just the second derivative of our wave function with respect to position, and the remaining terms are on the other side. And for the particle in the infinitely deep box, we have two regimes. We have inside the box, which has a potential equal to 0, and we have outside the box where we have an infinite potential. So these two different forms or different potentials are going to give two different solutions for the two different regions for the particle in the box. So first, let's start with outside the box. So what we're going to do is just plug in our potential in here for the potential energy term. So outside the box, that's going to give us that the second derivative of our wave function with respect to position is equal to minus 2m over h bar squared times E, the energy, minus the potential, which is infinity, times the wave function. So what we can do is realize that our potential, or energy minus an infinite amount of potential is going to be negative infinity. So we can swap that out for positive infinity and then swap out this term here. So we have 2m times h bar squared times infinity times our wave function. So this is going to pose a problem for us, and that's because our wave functions need to be normalizable. Remember, our wave functions don't have any physical meaning in themselves. Rather, they lead us to calculate the probability of finding a particle within a certain region. So if our wave function is infinite, then we can't calculate a meaningful probability. So our wave function can't be infinity. So that means the only way for this to work out is if, in this case, our wave function is equal to 0. So outside of the box, our wave function is equal to 0. Inside the box, that's not the case. So inside the box, our second derivative of our wave function with respect to position is equal to negative 2m over h bar squared times the energy, and now the potential is 0, and times the wave function. So here, we don't have to be 0, and we can think about how do we solve this. So we can realize that this is a simple differential equation where we need to take two derivatives of our function, and that needs to return our function multiplied by a negative constant. So there are two kinds of functions that fit this. One would be e to the ix, but that's going to be not the most useful form for this, and it turns out the more useful form is going to be a sum of sine and cosine terms. So our wave function here is going to be equal to a sine kx plus b cosine kx. And in this case, k is equal to all our constants here, the square root of that. So k is equal to the square root of 2m e over h bar squared. So one thing we can do first is I just gave you the solution, so we can verify that this actually is a solution to our problem. And we just do that by simply taking two derivatives. So first, let's take one derivative. So the derivative of our wave function here with respect to x is going to be equal to a k cosine kx, and then minus b k sine kx. All right, great. Let's take a second derivative. So this derivative of this with respect to x is going to be minus a k squared sine kx minus b k squared cosine kx. And in this case, we realize that we can just factor out a minus k squared. That's going to give us a sine kx plus b cosine kx, which means that this wave function is equal to minus k squared times our original function. And what's k? Well, k is the square root of 2me over h bar squared, and so negative k squared is equal to negative 2me over h bar squared. So it turns out that this function is a good solution to our Schrodinger equation here. So now we might want to know, well, what actually is our function? We have this k, we have a, we have b. What are these values? And we can solve for these values by introducing boundary conditions. And our boundary conditions here are going to be that our wave function has to be 0 at the boundaries. And that's because outside of the boundaries, our wave function is 0. So at the boundaries, it also has to be 0, so our wave function is continuous. Why does our wave function need to be continuous? Well, what happens if our wave function is discontinuous? So say we have a value here, and it's discontinuous and a function comes up here. Well, if I want to measure the probability of being at this location, if it's discontinuous, I have two different probabilities of being at that location. And that doesn't make any sense. So our wave function has to be continuous in order for it to give a meaningful probability. So we can set these boundary conditions. So that's going to be at the boundaries. So the psi of 0 has to equal 0, and psi of a also has to equal 0. And these are our boundary conditions that's going to make our wave function make physical sense. So first, let's go ahead and evaluate psi of 0 equals 0. So at psi of 0, we have a sine of 0 plus b cosine of 0 equals 0. Now sine of 0 is equal to 0 and cosine of 0 is equal to 1. So that gives us 0 plus 1, or b is equal to 0, which means b is equal to 0. So we can't have any cosine terms, and that again makes sense because at 0, that's equals 0. Cosine will not equal 0 at 0, only sine will. So no cosine terms in our function. And we can evaluate the remaining condition. So psi of a equals 0. And psi of a, again, b is already equal to 0. It's going to give us capital A sine of ka is equal to 0. Now, we have two options. One of the options is that a is equal to 0, but that's going to give us 0 wave function, so that's not a good one. The remaining option is, well, then sine of ka must be the part that equals 0. And sine is equal to 0 at every integer times pi. So that means that our function that's inside, our term that's inside the sine, our ka, has to equal n pi. Every time it's equal to an integer times pi, that's going to return 0. So here we can get that k is equal to n pi over a. Plugging that back into our function, we get that our wave function is equal to a sine n pi x over a. And this is the form of our wave function. It's these sine functions. Now, the last thing we might want to do is figure out what a is. And remember, a is just a constant that sets the normalization. And we have to be normalized again because we want our wave function to be a probability. We want that probability to be equal to 1, so it makes sense. So a is just some constant we need to multiply our functions by in order to end up having the total area under the curve being 1 and having a sensible probability. To calculate a, we simply need to integrate over our box dimensions 0 to a of psi star psi, and this has to equal 1. That's the definition of normalized. So we just plug in our wave function here and solve. So this gives us a squared, I'm factoring that out because it's constant, times the integral of 0 to a of sine squared n pi x over a dx. So this sine squared n pi x over a is a integral that we can look up the solution to. So we look up the solution to this function. We end up finding that it is x over 2 minus a over 4n pi times sine 2n pi x over a, and we're evaluating that from 0 to a. So first, we're going to end up with a sine, either sine of 0 or sine of 2n pi, both of which are always 0. So we can ignore the second term. And the first term, we're going to end up with a over 2 minus 0. So this gives us 1 is equal to a squared times a over 2. We're simply going to rearrange that and solve for a, and end up getting a is equal to the square root of 2 over a. So our total wave function is equal to the square root of 2 over a, and then sine n pi x over a, where n is any integer. And these are the solutions to the particle in a box. Now, one thing we can do with them is go ahead and go back up to our box and actually draw the solutions in. So I'm going to give us some energy levels, and we'll calculate the energy levels next. Let's erase these V's. All right, so the first energy level, remember they all have to start and end at 0. Whoops. So they're going to start at 0, and when n is equal to 1, that's going to be a half integer sine curve. So it's going to go up, and it's going to come back down and end at 0. And then when it's equal to 2, it's going to be a full integer, a full sine curve. So it's going to go up and then come back down. And then for n equals 3, it's going to go up and down and up and back down. And these are the solutions, and they'll go on and on towards infinity. But you can see that I've drawn some energy level spacings here. And how did I come up with those? Well, to come up with the energy level spacings, you simply need to use the Schrodinger equation. So the Schrodinger equation has our Hamiltonian operator. We operate on our wave function, and what we get out is our wave function multiplied by a constant, where the constant is equal to the energy. So we'll come back down here and write that. So our Hamiltonian is equal to negative h bar squared over 2m times the second derivative with respect to x, and then plus the potential. In this case, the potential is equal to 0. So all we need to do is take two derivatives of our function and then multiply by negative h bar squared over 2m. So we'll do that. So we operate on our wave function here, and that's going to give us our energy as a function of n times our wave function again. So two derivatives of this wave function are simply, it's going to be sine again. We're going to pull out that term inside, that n pi x over a. We're going to pull that out twice. So the second derivative of our wave function with respect to x is equal to n squared pi squared over a squared times our wave function again. So I'm going to plug this term here into the Hamiltonian. So we'll get negative h bar squared over 2m times n pi over a squared times our wave function. And that's equal to the energy times our wave function. Here our wave functions cancel out, and we finally have an expression for energy. So our energy is equal to, this is equal to negative there, so we lose that negative as well. So the energy is equal to h bar squared over 2m times n pi over a squared. Now we'll do some simplification here. We'll recognize that h bar is h over 2 pi, and that allows us to cancel the pi squared. And when we do that, we end up with h squared n squared over 8ma squared as the energy values for the particle in a one-dimensional finite box. So this is the general strategy that you use to calculate the energy values and the eigenfunctions for any quantum mechanical system that you are interested in.